Collisions in one dimension going to be the topic of this lesson in my brand new general physics playlist, which will eventually cover a full year of university algebra-based physics. Now in this lesson we're going to talk about three types of collisions: elastic, inelastic, and perfectly inelastic. And we're going to take and learn a structured approach for how to solve calculations involving collisions. My name is Chad, and welcome to Chad's Prep, where my goal is to take the stress out of learning science. Now, if you're new to the channel, we've got comprehensive playlists for general chemistry, organic chemistry, general physics, and high school chemistry. And on chadsprep.com, you'll find premium master courses for the same that include study guides and a ton of practice. You'll also find comprehensive prep courses for the DAT, the MCAT, and the OAT. So collisions in one dimension. So if you're intuiting that in the next lesson we'll be covering collisions in two dimensions, then you'd be exactly right. So we're taking the same approach we did with Newton's laws of motion, where we'll learn how to apply, use free body diagrams and set up the sum of the force equations and take a structured approach to solving Newton's laws problems in one dimension, and then applying it to two and finding out that the problems really aren't that much harder, but they are longer. Same thing's going to be true here for going from collisions in one dimension to collisions in two dimensions. So starting off in one dimension. So before we actually learn that structured approach, we got to define and describe three different types of collisions. We've got elastic collisions, and then we've got inelastic collisions, and then a special type of inelastic we call perfectly inelastic collisions. Now to describe these first off, so for an elastic collision, so for two objects to collide elastically, we say, so they have to have no propensity to stick together whatsoever, just bounce right off, no stickiness whatsoever, if you will. If you look at the other end of the spectrum, the perfectly inelastic, so now not only do they have a propensity to stick together, they absolutely stick together after the collision and then move together after the collision. That is perfectly inelastic. And then plain old inelastic is somewhere in between. We're not going to stick together completely after the collision, but we don't have no propensity to stick together whatsoever either. It's somewhere in between. Now those are descriptions, and typically for perfectly inelastic, that's part of the description you'll get. For the other two, not so much. What you will get, though, is something more akin to the permanent definition. Now it turns out for any collision, momentum is going to be conserved, that we're going to study about in this section. So if we learned about in the last section that in the impulse momentum theorem, that if there's a net force acting on an object, then it's going to lead to a net impulse, which is going to cause a change in momentum. Well, we can kind of look at the converse then. If there's no net force acting on an object, and then there's no impulse and no change in momentum. So in this case, we'll be applying it not to just one object, but to a collection of objects, usually two, that we're going to call a system of objects. And if there's no net force acting on that system, so then there's going to be no impulse and no change in momentum, and so we can say that momentum is conserved. And so for two objects colliding, which is going to be the most common circumstance we'll look at, as long as there's no net force acting on the system of objects after the collision, so then momentum is going to be conserved. And so for every one of these three types of collisions we're going to encounter, that's the first part. We're going to say that momentum is conserved. And so for an elastic collision here, we'd say that P initial equals P final. And for both inelastic and perfectly inelastic, we'll say the same thing. So initial momentum is going to equal final momentum. So that is always going to be true. And that's generally going to be the first equation you set up. And so for two objects, you're typically going to have like an m1v1 initial plus m2v2 initial equals m1v1 final and m2v2 final. So that's kind of how that's going to play out. Same thing again with the inelastic. Now the difference here is when two objects collide and they have no propensity to stick together, so it turns out that kinetic energy will also be conserved. And so that's going to be true for an elastic collision as well. Your initial kinetic energy will equal your final kinetic energy. And again, you'll split this up usually across two objects is typically how this will work. And so you'll have 1/2 mv1 or m1v1 initial squared plus 1/2 m2v2 initial squared equals 1/2 m1v1 final squared plus 1/2 m2v2 final squared. So, and those are the equations we're going to kind of set up for an elastic collision. Whereas for an inelastic or perfectly inelastic, kinetic energy is not going to be conserved. You're always going to have a loss of kinetic energy. And it turns out if the two objects stick together, as in a perfectly inelastic collision, that is when the maximum loss of kinetic energy is going to occur. And so there's no second equation here for kinetic energy for these inelastic collisions, whether it be plain old inelastic or perfectly inelastic, all we have is that momentum is conserved. But this gives you a great place to start for any collision problem. You're always going to start by setting up an equation for momentum being conserved. What we'll find out though in 2 dimensions, well, momentum we learned in the last lesson is a vector. So in 2 dimensions, you're going to have to break it up into x and y components. And so you're going to end up having momentum conserved in the x dimension and momentum conserved in the y direction. And so you'll have 2 conservation of momentum equations. So, and then potentially what's nice is that kinetic energy is not a vector. And for elastic collisions, you'll only still just have the one kinetic energy being conserved equation. So potentially instead of 2 equations for elastic collisions, you might end up with 3. And then for inelastic and perfectly inelastic, you might end up with 2 equations instead of just 1, again, breaking momentum up into x and y components. All right, let's learn how to do this in the context of some problems here. All right, so first problem here says, a 100.0 gram blue ball is moving north with a velocity of 10.0 meters per second toward a 100.0 gram red ball, which is moving south with a velocity of 2.0 meters per second. After they collide, the blue ball is moving north with a velocity of 2.0 meters per second. What is the velocity of the red ball after the collision? Is the collision elastic or inelastic? So we can see that our blue ball is definitely slowed down here. So what we don't know is even what direction the red ball is. Now you probably can intuitively think, I bet you that red ball's heading north as well. And you'll be right, it turns out. So, but don't let your intuition kind of set everything in stone for you. So work the math out. It'll confirm your intuitions or contradict them in some cases. All right, so we don't know what kind of collision this is. So we're, the second part of the question is the collision elastic or inelastic? So, well, if we don't know if it's elastic or inelastic, we don't know one thing. We don't know if kinetic energy is going to be conserved. But what we do know is that for any collision, momentum is always going to be conserved. And so you can always start there for any collision problem. Momentum is going to be conserved. And so we can say that the initial momentum equals the final momentum. That's true. We can always set up that equation. And we've got 2 balls here, so we can set that up. And what we got to account for as well is that north, I'm going to make the positive direction. South, I'm going to make the negative direction. Because again, momentum is a vector, and so the direction is going to matter. And so if we set this problem up, so for the blue ball, we've got an initial, I'm going to leave the sig figs out of my calculations here, but I will account for it when I get my final result here. So, but 0.1 kilograms times 10 meters per second, that's its initial momentum. Its final momentum, so again, 0.1 kilograms times 2 meters per second. And this is positive 10 meters per second and positive 2 meters per second because it's north in both cases. All right, then for the red ball, also weighs 0.1 kilograms. Notice we had to turn that 100 grams into kilograms. So, and in this case, it was traveling 2 meters per second south. I'm going to make that negative 2 meters per second. And so there we have both momentum terms for the initial conditions, and we got to set it up for the final here. And again, we're just going to have plus 0.1 kilograms times velocity final of the red ball. I'll call it velocity red final. Well, I could have just called it velocity final because it's the only variable in the whole equation, and we can simply solve for it from here. Cool, so the one thing we're trying to find is what is the velocity of the red ball. The only equation we could set up is the only one we need to solve for that one variable. So let's go ahead and solve that. So as kind of is my custom, I use nice numbers that in many cases you can avoid your calculator with when possible. So we can not lose the forest through the tree, same thing true here. So 0.1 times 10 is going to be 1 kilogram meter per second. 0.1 times negative 2 is going to be minus 0.2 kilogram meters per second. And that's going to equal 0.1 times 2 is going to be 2 kilogram meters per second plus 0.1 VRF. I defined it. All right, so here we can take 1 minus 0.2 is going to be 0.8. We'll subtract off, that should have been 0.2. Subtract off another 0.2, and that's going to be 0.6 kilogram meters per second equal to 0.1 times the velocity of the red ball final. We'll divide by 0.1, and we can see that the velocity of the red ball final is going to equal 6.0 meters per second. We want 2 sig figs. It comes out to exactly 6, so we'll write it as 6.0. And there's your velocity of your red ball. Cool, and we can see that because it came out positive, that means it is in the northward direction. So the velocity is technically 6.0 meters per second north. Now the second part of the question is the collision elastic or inelastic? And that all comes down to, was kinetic energy conserved, yes or no? Well, we can go back to the problem before and after. We can kind of work this out. Now keep in mind kinetic energy is again 1/2 mv squared. We can just kind of sum this up before and after and see if it comes out the same. So, and again, there's no vector here for kinetic energy. It's a scalar, and so direction does not matter. So if we look at this, we've got, for the blue ball, let's start, we've got, actually we'll start for the red ball, why not? It's on top. So 1/2 0.1 and times the velocity of squared of 2 squared. I'm gonna leave off the units for ease here, but they're all SI units. So, and then here, 1/2 times 0.1 times 10 squared. So, and then after, well, for the blue ball, we can see that it's 1/2 0.1 times 2 squared. And for the red ball, from what we know now, it's going to be 1/2 times 0.1 times 6 meters per second squared. And the question is, does the total before equal the total after? Well, I can see that this term right here is equal to this term right here. So, but this term and this term are definitely not equal. This one is larger than this one. So the sum of these two is not going to equal the sum of these two. And so in this case, kinetic energy is not conserved, and therefore the collision is not elastic. It must be inelastic. Now in this case, the two balls did not stick together, so it would not be a perfectly inelastic collision, but it is an inelastic collision since kinetic energy was not conserved. All right, so the second problem here is going to be rather similar to the first one with one key difference, as we'll see, but it says a 100.0 gram blue ball is moving north with a velocity of 10.0 meters per second toward a 100.0 gram red ball moving south with a velocity of 2 meters per second. After they collide, the balls stick together. What is their final velocity? And that's the difference. So after they collide, they're sticking together, and that should be your big clue that, oh, this is a perfectly inelastic collision, one in which the two objects stick together after the collision. Now the setup is going to be the same. We're going to start with conservation of momentum, the same way we'll start with any collision problem here. So, but we'll see that the result's going to look just a little bit different. All right, so we'll start here with initial momentum equals final momentum, our condition of conservation of momentum. So, but the final result's going to be a little bit different. So we've got m1 v1 initial plus m2 v2 initial is going to equal m1 v1 final plus m2 v2 final, except for the fact that the balls are moving together at the end. And so it turns out that the V1 final and the V2 final are the same velocity. They're moving together. And so as a result, we can kind of factor it out and make this look like a single term with just V final. Instead of V1 and final and V2 final, there's just a V final. And then factored out between it will be M1 plus M2, the total combined mass of the objects that are now stuck together. And that's what it's typically going to look like for a perfectly inelastic collision as a final result. And again, you can derive it every time. You can just set it up every time. So, but if you kind of know where it's going from the get-go, it'll save you some time in solving the problem. And from here, it'll just be plug and chug. So we've got 0.1 kilograms again, times 10 meters per second, plus 0.1 kilograms times, again, -2 meters per second. And this is now going to equal, well, 0.1 kilograms plus 0.1 kilograms is now a combined 0.2 kilograms. And then again, times that final combined velocity. And from here, it's just plug and chug. So 0.1 times 10 is still 1, and that's kilogram meters per second. So plus 0.1 times -2 is minus 0.2, or plus a -0.2, if you will. And that's going to equal 0.2 kilograms times that V final. And 1 minus 0.2 is going to be 0.8, and then we'll divide through by the 0.2, and 0.8 over 0.2 is going to get us 4.0 meters per second for that final velocity of the two balls moving together. So because it came out positive, that means it's in the northward direction. So your intuition was correct if indeed you thought, oh yeah, they got to be moving north after the collision, since the blue ball was moving faster in the northward direction than the red ball was in the southward direction. Great. So, and we can definitely see that kinetic energy is definitely not conserved yet again. So if we look again before and after, so before we didn't have 1/2 times 0.1 times 10 squared plus 1/2 times 0.1 times 2 squared. And after, we have 1/2, and the mass is now 0.2 times 4 squared. So, and you can definitely see that this is going to be much lower than this, and you'll find out actually it's even lower than the last problem, because this is where we're going to lose the maximum amount of kinetic energy in a perfectly inelastic collision. All right, so next question will be the last one involving a blue ball and a red ball, I promise. So next one says a 100.0 gram blue billiard ball is moving directly toward a stationary 100.0 gram red billiard ball with a speed of 10.0 meters per second, resulting in an elastic collision. What is the velocity of both billiard balls after the collision? So a couple key things here. So one, we are told this is an elastic collision. And so not only is momentum conserved, but kinetic energy is also going to be conserved. And so we can set up a conservation of momentum equation, and if we need it, then we can also set up a conservation of kinetic energy equation, and we're going to find out that it is needed in this case. Also, I called these billiard balls. In the last two examples, I just called them balls. But here I called them billiard balls. And it turns out that billiard balls, they have almost no propensity to stick to each other. They don't really deform in any way, shape, or form. And so a very, very minuscule amount of kinetic energy is actually really lost in the collision of billiard balls. And so they're kind of our best example of something that's almost what we would call an elastic collision. Now, they're not completely 100%, they're just like 99.9% elastic. So, but we use them as the classic example of elastic collisions all the time. And so if you see billiard balls colliding, you should think that's probably elastic. Or if the question just plain old tells you it's an elastic collision, then assume it's an elastic collision. So that's the key here. So always start with momentum, and we'll start there. It's the easier of the two equations, but it's one that's always true regardless of the type of collisions. And so we'll start with the conservation of momentum here. And so here we're going to have initial momentum equals final momentum. So, and again, momentum is mass times velocity. And what's nice is that the initial velocity of the red ball is 0, and that term is going to go away. And so we're going to end up with, in fact, I'll write it out once. So m1 v1 initial plus m2 v2 initial equals m1 v1 final plus m2 v2 final. And in our particular example, one of those terms is going to be 0 for sure, with no initial velocity for the red ball. It's stationary. Okay, and then we can do some plugging and chugging, and I'm going to leave off all the units because we got a lot of algebra to do, and the units just get in the way, but I'm using all SI units for everything. So for mass, 100.0 grams is going to be 0.1 kilograms. And so we're going to have 0.1, and then the initial velocity of 10 meters per second for the blue ball. And then that's going to equal, again, 0.1. So, and then we don't know the final V1 velocity, and then 0.1 for the red ball, and we don't know the final velocity for that either. And so in setting up our conservation of momentum equation, we have two variables, but we've only so far got one equation. Well, again, standard practice in algebra, for every unknown you want to solve for, you need an equation. So if you've got two unknowns, you're going to need two equations. So far, we've got just one. But again, we know it's an elastic collision, so we've got a second equation. We can set up the conservation of kinetic energy. And so we'll do exactly that. And so now kinetic energy initial equals kinetic energy final. So, and once again, one of these terms is going to drop out, but if we see the way this sets up, so 1/2 mv1 initial squared plus 1/2 mv2 initial squared equals 1/2 I should be writing m1 and m2, but m1 v1 final squared plus 1/2 m2 v2 final squared. Once again, the initial velocity of the red ball is 0, and so this term is going to end up being 0. So that'll save us a little bit of time on the setup and stuff like this. There'll be one other thing that we can take advantage of. We can take advantage of it now, but we can also take advantage of it later, as we'll see. And I'm going to reserve it for later here to simplify this in just a second. So, but if we plug the numbers in now, we got 1/2 times 0.1 kilograms again, times 10 meters per second. Don't forget to square it. And that's going to equal 1/2 times 0.1 times V1 final squared plus 1/2 times 0.1 times V2 final squared. Okay, so now we've got two equations. We've got conservation of momentum has led us to an equation, conservation of kinetic energy has led us to an equation, and they both have the same two variables which we can now solve for. Now I'm going to make a suggestion here. So this is, V1 final and V2 final. This is V1 final and V2 final, but we know the initials. And so the final label doesn't really serve a purpose for us. It's the only one we don't know is the final velocity for both. So I'm just going to simplify this down to V1 and V2. They are final velocities. I just want to make this a little bit easier to solve and not kind of lose the forest of the trees when we're doing the algebra here. And that's why I've also, again, left off the units. All right, so how do we solve this system of equations? So easiest routes probably do some form of substitution. Notice this one involves squares. And solving for something when you have a square term means you're going to have a square root and substituting in, and that's going to look really ugly. So I would not recommend going that route. So we'll definitely solve one of these for either V1 or V2 and substitute it into the other one. It's the route I recommend. And so that's the route we'll go here. So in this case, 0.1 times 10 is 1. And so we're left with 1 equals 0.1 V1 plus 0.1 V2. And it doesn't really matter which one we solve for. I'm going to solve for V1 here. And so we're going to end up with 1 minus 0.1 V2 equals 0.1 V1. And if we solve for V1, we'll divide by 0.1. 1 over 0.1 is 10. And 0.1 over 0.1 is 1. So 10 minus 1 V2, which is 10 minus V2, equals V1. And now we're ready to substitute this in to our equation over here for V1. Right there. All right, so one other thing we can do to simplify this, and we could have technically considered it up here as well. We could have made our lives a lot easier. If every term has a common term, then you can factor it out, or in this case, really divide it out of the entire equation. We could have actually just gone and said, well, every term has a 0.1 and got rid of it. And it would have saved us a little bit of math. So it wouldn't have been the biggest deal, but here it actually is going to save us a substantial amount of math. So we're definitely going to factor it in. Every term's got a 1/2. And again, every term has to have it. If just one of the terms doesn't have it, you can't factor it out. So we'll divide that out, but also every term has a 0.1 in it. And so we can factor that out as well. And so what does this reduce down to? Well, 10 squared is 100. So, and that's going to equal V1 squared plus V2 squared. And this looks a lot easier all of a sudden. And again, we're going to substitute in 10 minus V2 for V1. And so we're going to left with 100 equals 10 minus V2 all squared. So there's V1 substituted in, and then plus the final V2 squared. And then we got to FOIL out the square, or if you kind of know the way for expanding squares. So 10 squared is 100. And a square of a binomial, it's one term times the other times 2. So 10 times negative V2 is negative 10 V2 times 2 is negative 20 V2. And then negative V2 squared is positive V2 all squared. And then plus your final V2 squared. All right, so there's the equation we have to solve. And in this case, we can subtract the 100 from this side, and those terms go away. And we're going to be left with 0 equaling, and I'm going to put the v squareds first, kind of put it in a quadratic looking order. So that's going to be 2v2 squared minus 20 v2. And that equals 0. And we don't have a c term in our quadratic here. We've got, ax squared plus bx, but there's no c equaling 0. And it turns out we can solve this without actually having to use the quadratic equation. So let's factor out a v2 there. So in this case, if we factor out that v2, we're going to have v2 times 2 v2 minus 20. And I'm going to write it around the other direction, equals 0, same diff. Well, in this case, you've got two terms multiplied together to give you 0. There's two possible solutions. Either this term is 0 or this term is 0. Those are your options. And so when we solve for this, well, one option is simply that v2 equals 0. That's one option. Or the other option is that 2v2 minus 20 equals 0. And so there's two possible solutions, and we have to distinguish between which one is a real solution and which one is just a mathematical solution, as we'll see. All right, for the second one here, we add the 20 to the other side and then divide by 2. We'll find out that V2 equals 10, and I'll put the unit back on, 10 meters per second. So the question is V2 0 or is V2 10 meters per second? Well, let's look at this. So V2 is this guy right here. What's his final velocity? Well, if the blue ball hits the red ball, what are the odds that it continues not moving? Well, I mean, if it was glued down or something, I guess we could assume that. But otherwise, that's not a real solution to this problem. It's a mathematical solution, but it's not a real physical solution, we say. And so the truth then must be that V2 equals 10 meters per second. All right, and with V2 is 10 meters per second, we can substitute it back into either one of our equations, and I personally like the one that doesn't have squares in it. We can substitute it right back in here and solve for V1. Well, 10 minus 10 is 0, and this is going to tell us that V1 is actually equal to 0. And so in this case, we see what happens is this blue ball is moving with a speed of 10 meters per second, hits the red ball, and stops. Transfers all its kinetic energy into the red ball, all its momentum into the red ball, and now the red ball's moving in the same direction with a speed of 10 meters per second. This is a common result in billiard balls involving an elastic collision. So a common problem you'll probably encounter somewhere again besides just this video. Cool. But this is how you solve that system of equations. And again, I gave you an example that we didn't actually have to set up and solve a quadratic, but you should be prepared to do so. Good chance it shows up in your homework somewhere along the way. And for some of you, it may even have a chance of showing up on the exam, although some professors will realize just the time involved and eliminate it, but not all. So be prepared. All right, so the last question here is going to be a little bit more challenging. It's an old-fashioned way of determining the velocity of a bullet. And what's going to make it more challenging is kind of putting what we've learned in this chapter in the broader context of everything we've learned. So we've learned about collisions and how we deal with the conservation of momentum in collisions and things of the sort. However, it's going to put it in the context of what we learned in the last chapter about energy, and specifically about the conservation of mechanical energy, and incorporate that as well, as we'll see. So the question says a bullet with a mass of 10.0 grams is fired horizontally into a 990.0 gram block hanging vertically from a 1 meter long wire. The bullet's going to become lodged in the block, which subsequently is going to swing upward with the cord making a maximum angle of 60.0 degrees with the vertical. What was the initial velocity of the bullet? So the idea is that for a given bullet of a given mass, the faster it's fired, then eventually the higher this bullet block combination is going to swing up. And we can back calculate how much that's going to be. Well, if we take a look, so for this last part, so the bullet block combo has a certain velocity at the time the bullet becomes lodged in the block. So, and its velocity, so kinetic energy, is going to get converted all into potential energy as it swings up. But mechanical energy is going to be conserved. Well, going back then before that, so the bullet is fired into the block and it lodges in the block. They become stuck together. One, that is a collision, and because they're stuck together, what kind of collision is it? Yeah, it's a perfectly inelastic collision. And momentum is going to be conserved, but kinetic energy is not going to be conserved. And so for the second half of the problem, we'll be dealing with the conservation of mechanical energy. For the first half of the problem, we'll be dealing with a perfectly inelastic collision where momentum is conserved instead. And you kind of got to work it backwards here. And so for the end, with conservation of mechanical energy, we have kinetic energy initial plus potential energy initial equals kinetic energy final plus potential energy final. Well, if we look, this bullet block combo starts at the lowest point and then swings upward. Well, if that's the lowest point, we might as well define that as the zero height, which means initially here, we've got no potential energy. And when it swings up to its maximum height, for a brief instant, it has a velocity of 0. And so the final kinetic energy up here is 0. And so we just end up with initial kinetic energy equals final potential energy, a result that's similar to the ones we've seen in the last chapter. So if we set this up, we've got 1/2 mv initial squared equals mgy final. and we want to solve for that velocity of the bullet block combo. Now, if you're going to plug a mass into this, it's got to be the mass of not just the block, but the bullet block combo, the 990 plus the 10, 1,000 grams or 1 kilogram. But in this case, we don't have to, because mass is going to fall out anyways and cancel. All right, if we see the result here, so we're going to get V initial squared equals 2G Y final. And so V initial is going to equal the square root of 2G Y final, a result that's similar to something we've seen before. Now, to figure out what that final height is, we want to know, well, going back over here, how much higher is it than our zero height, if you will? Well, got to use your trigonometry here, and so we can see that this adjacent side right here would be the 1 meter times the adjacent side, so cosine of 60. So, and I use this on purpose because the sine of 30, if you recall, is 1/2. Well, the cosine of 60, the complementary angle, is also 1/2. And so 1 times 1/2, 1 meter times 1/2, shows us that this distance right here is 0.5 meters, which means that this distance is also 0.5 meters for that total 1 meter thing. So our height above our 0 point here is an additional 0.5 meters. And now we can solve for that velocity. All right, we'll definitely use our calculator for this. All right, 2 times 9.8 times 0.5, and then I'll take the square root of that result. We're going to get 3.13, and if you notice, it's 2 times 0.5, 2 times 1/2 is 1, so it's really just the square root of 9.8. And the square root of 10 is like 3 and some change, so the square root of 9.8 is 3 and some change. 3.13 meters per second. Okay, so we're halfway there. We now know that the velocity at this point was 3.13 meters per second. At the moment the bullet becomes lodged in the block, they were moving in unison at 3.13 meters per second. And for the second half of the problem, that was the initial velocity. But for the first half of the problem involving the collision now, the perfectly inelastic collision, that's the final velocity. So we got to set up our conservation of momentum now. And so now initial momentum equals final momentum. And we're going to have m1 v1 initial plus m2 v2 initial equals m1 plus m2 times v final. If you recall, for a perfectly inelastic collision where the two objects stick together, so the product side here for momentum is going to have a combined mass times their combined velocity since they move together. All right, we can simplify this down a little bit as well because initially the block is not moving, so no velocity there. And then go from here. So we've got 0.01 kilograms times an initial velocity that we don't know, we want to solve for. And that's going to equal, and again, 10 grams plus 990 grams is 1,000 grams or 1 kilogram. And again, I'm leaving off units so we don't get lost in the trees. Oh, and then times the final velocity, which was the initial velocity for the second half of the problem. So 3.13, I said I was leaving off units, but whatever. All right, so if we want to solve for V1 initial now, we have to divide by 0.01. Well, dividing by 0.01 is the same thing as multiplying by 100. So here we're going to get 313 meters per second. And in this case, we're going to want 2 sig figs. So we'll round that 1 down and keep it a 1. And so V1 initial velocity of the bullet is 310 meters per second. Cool. So if you notice a diagram, super crucial. So diagramming out each half of the problem separately is super helpful as well. So, but again, this is one that students really struggle with first time around, usually need a little help towards the right direction. Hopefully this helps. If you have found this helpful, consider giving the video a like. Happy studying.